Let's continue our discussion about transistors. Okay, so first we're gonna take some recap about what we have taken so far. Okay, so this is again the structure of the transistor. And we have 3 terminals. And we said that for amplification, we need an active, we need the transistor to work in active region. So in active region, this junction G1 should be forward. Enough forward even, I mean, it should have at least 0.7. Okay, if it's a diode, it will be on. That's what I mean. And J2 should be reverse for zero bias. J2 reverse, or let's call it zero bias for now. But we will see in this lecture, it might be forward bias, but the voltage is small. Okay, less than 0.4. We're gonna see this. So this is a collector. And to do that, to make J2 reverse, we connect a battery like this, okay, between the collector and the emitter. Here is the doping is heavily doped. Here is normal doping and also normal doping for the collector, okay. And we say that to maintain or sustain G2 in reverse and G1 in forward, VCE, there was a condition that VCE should be greater than 0, okay, to sustain G2 reverse. Okay. VBE, I said that this junction should not be should be forward, and we can say strong forward. Okay. I mean, if it was a diode, it should be on. So VBE should be between 700 to 800 millivolt, or between 0.6 and 0.8, 0.7 and 0.8. Okay. What also we have? Yeah. And also in active region, we have these relations that IC equal to beta IB. Okay. And IE, the emitter current, is equal to IC plus IB. There is another factor or parameter called alpha. And alpha is equal to beta over beta plus 1. So it's close to 1. I didn't mention this just for good. Okay. So what is actually this beta? So here IE is equal to IC plus IB. IC equal to IC plus beta IP. So it's equal to IC. I'm sorry. Want to relate IE and IC. It's the opposite. So yeah, IE equal to IC plus IC over beta. Okay. So from this, you will find that IC equal to beta over beta plus 1 multiplied by IE. And this is called alpha, our new parameter alpha. It's just, dependent on beta. If you have alpha, you can get beta. If you have beta, you can get alpha. That's it. Okay? Nothing new, I mean. What else we have? Yeah, we have the relation also between IC and the voltage here, this VBE voltage. It's equal to IS exponential VBE over VT. And IS in that specific relation is equal to the area, but the area in specific of the emitter. Okay? So the structural geometry of the transistor might be different between, the area and the cross section and stuff might be different between the emitter and the collector. And we see here there is also a difference in the doping. So it also might be predicted or anticipated that also the geometry is different. So the area of the emitter, the cross section of area of the emitter, multiplied by Ni squared Q, the diffusivity or the diffusion parameter that we took in diodes, over the doping in the base, multiplied by the width of the base. Okay. Finally, in active region, if we want to draw the characteristics between IC and VBE, it will be something like this, just like a diode. Okay. And just one note here, when we draw these characteristics, we should fix VCE. So VCE here is constant. We will see later that IC is changing with VBE as we took, and also VCE in some context. So we always fix one and change the other to draw its characteristic to with IC. Now, until this moment, the relation between IC and VCE is just constant. It's not, IC is not dependent on VCE, in active region at least. So, for example, if we fix VBE at some value, call it VBE, okay, and we increase VCE, we got a constant like this. If we increase VBE, so for example, VBE dash, IC will increase, but then if you change VCE again, IC will be fixed. If you decrease VBE to, let's say, VBE double dash, IC will decrease. Okay, if you fix VBE double dash and change VCE, you will get also some constant like this. Now, what's happening really here? This is the missing part in the characteristics that we're gonna fill today. So let's start let's examine now the operation of the transistor in another region called saturation region. So saturation region of the transistor, in which we're gonna, fill this missing part. So in saturation region, so in active, G1 was forward and the G2 was reverse. And remember, G2 is dependent on the voltage VCE. So to sustain G2 as reverse, VCE has some condition to be larger than 0 or something. Okay? Now what happens if we decrease this? So gradually, G2 will turn from reverse into forward. So let's see now the conditions or the operation when G1 and G2 both are forward. And this is happening when VCE decreases. So when we gradually decreases VCE, G2 gradually turn to forward. Okay. But forward for G2 is not enough. We want to see the operation when G2 is strongly forward. I mean, there is a current flowing, because if we look at let me draw it here, the characteristic current of the diode, the characteristic plot of the diode, it will be something like this. So for some region in here, the current is very small. Some engineers, in literature, I mean, some consider this around 0.4. After 0.4, you will see some noticeable observer or remarkable current. And before this, the current is very small, almost zero. Okay. This is just a rule of thumb. This is 0.4. Somebody may say, no, it's 0.3. You know, just after some value, whatever it is. Okay. So we're gonna examine now J2, the junction between the collector and the base, when it has voltage larger than 0.4. VBC is the voltage between the base and the collector, which was reversed before in active region or zero. Now in this region, it's larger than or greater than 0.4. Let's see what's gonna happen. So again, here is our, base, collector, and Mr. emitter. And, we don't need to just so now G2 is forward and conducting. I mean, the voltage is larger than 0.4, so there is a current. And G1 is forward again. Okay. G1 is the same, has something between 0.7 and 0.8. So the original situation is as follows. We have some, electrons, as we said last lecture, flowing from the emitter to the base, then they will be attracted to the voltage VCE. Okay, and we have small number of holes going from the base to the emitter. And we said that when you have asymmetric junction with some part heavily doped, so this heavily doped part will emit more electrons if it's N of it, or if it's B, it will emit more holes than the other side. And we said that I hole is less than I emitter. I electrons. But now this junction is also J2 is also forward. So there will be also electrons coming from the collector to the base, and also holes going from the base to the emitter, to the collector. So let's see what will be the implication of that. So there are two implications, or two consequences, or two, whatever you call it, two consequences. Number one. So remember IB, which is flowing loads. Let's draw here the VB and Mr. VC. Remember there is IB that is going in that way, and IB was actually equal to IH, I hole. Okay. Now there are holes going downward and upward. So IB should increase. So IB should increase. Just imagine it. In the beginning, it was going in that way, then go down. Now it's going down and also up. So IB should compensate for the holes that is going down and the holes that is going up. That's it. In the beginning, we have only holes going down. Now we have from the base emits holes or send holes to the emitter and also send holes to the collector. So IB should compensate those currents. So IB should increase. But how about IC? In the beginning, without these, let me have another card. Without these electrons, the IC came only from these electrons that came from emitter to the collector, base and then collector. But now no. Now there is another hole electrons going in the opposite way. Okay, so now there will be a net current, and this will be subtracted because they are in the opposite directions. Okay, so IC, okay, will decrease. Okay, okay. In the beginning, when in active region, IC over IB is equal to beta in active region. This is inactive. Now, what will happen when, if for this relation in saturation? So let's draw it, let's write it again. So IB will increase, IC will decrease. It's a twofold effect. The numerator decreases and the denominator increases. So this for sure will be less than beta. Or in more specific, less than or equal to, because you know there is a point at which it's like a transition point. You remember with diodes, this point between off and on, something like this. Okay, so these are the two consequences that will happen when J2 become, we can say not a strong forward, but at least the forward is conducting forward. Let's call it that way. Okay, so now if we're gonna extend the characteristics between IC and VCE, I'm sorry, VCE. So let's draw it now. This is Mr. VCE, and this is Mr. IC. So in the beginning we had, 3, for example. We can of course have many, like what we see in the lab. We're gonna construct these characteristics, of course. Now, when VCE started to decrease, and this happens at very small values, as we will see now, okay, IC will decrease. So I'm gonna go down like this. Semi-linear, you can say. So this is the saturation region. And here is the active region. Okay. These transition values here are between 0.3 and 0.1 volts. Okay. In saturation region, so let's now conclude the new relations or equations that we stated from active now in saturation. So in saturation region, we have the following. Number one, VBE is still between 0.7 to 0.8. No change. Okay. VCE, the voltage, if this is VCE, it would be very small. As you see here, these values are small. Okay, so in deep saturation, it's usually around 0.2 volt. This is just a rule of thumb. This doesn't mean if you know that's a transition saturation, if you measure something like the 0.7 that we always assume for the diode. Okay. And we can say the point of transition, let me get the correct term for it. I don't have it, but anyway, that's fine. So the transition happens, we can say the transition from active to saturation happens at almost approximately 0.3 volts. Okay. What else we have? We still have IE equal to IC plus IB. No change in that. But now we have IC over IB less than or equal to beta. Okay, not equal to beta. What else we have? Yeah. Finally, VBC, the voltage between this voltage between the collector and the base, VBC. This voltage is forward voltage. And as a rule of thumb, it should be larger than or greater than 0.4. That means if VBC is less than 0.4, GT was forward. But we can say we are not strongly active, not strongly saturation, but we still somehow active because the current in that flowing from the base collector junction is small. Okay, so let's say that in active we want only one junction that conduct current. The other shouldn't contribute in the currents. So IC and IB will not change, will not increase or decrease. So IC over IB will be equal to beta. Okay, so that's the point behind that. Okay, now let's see now the first model. Now we wanna put this transistor in a circuit and we wanna solve it. Okay, so just like what we did with the diode, we have the equations now, so we can put it in a circuit and solve it. To make it easier to solve, we could also make a model for the transistor, so we can because it's a complex, it's not just like a diode, because it's a complex structure, a complex device, we can remove the original symbol from the circuit and put some equivalent circuit for it to make it easier for us to solve. Okay, also after a while, if you train yourself a lot, you will find that you are just dealing with the transistor symbol itself in the circuit and no need to draw any equivalent circuit for it. But let's see what is this model for it. So this is called the large signal model, and this is, we can say, the general model of the transistor. Okay, it can be used all the time. As we will see in the next lecture, there will be something called small signal model as well. That is used only if the input is very small. Okay, but this can be used if the input is large or small, whatever. So we have for the transistor, this is the symbol for it. We have base, we have collector, we have emitter. So whenever you have a model, you should have these three terminals: base, collector, emitter. So between the base and the emitter, there is in active region. This is for active region. Yeah, let me write this to make it this is for active region. We have a forward junction, so it can be represented by a diode. And the voltage is VBE. And between the collector and the base, the junction is either reverse or even forward, but with very small current or even neglected. So it can be represented as open circuit because G2 is reverse or off, more general off. This is forward, G1. And between the collector and the emitter, remember we said that with transistors, we succeed to implement or create a voltage dependent current source, which is IC, right? So this is IC, which is current voltage dependent current source. So This is IC equal to IS exponential VBE over VT. And from now on, we will neglect the one. So the exact one is exponential VBE over VT minus 1. We will neglect this one from now on. I will not write it again. Okay? Just to make our equations easier to write. And here is Mr. IC flowing in that direction. And here is Mr. IB. Okay, and remember, they are merged in the emitter. So IE is equal to IC plus IB. Okay, this is inactive. Good. How about saturation? So in saturation, we have something similar, except that we will add, one more diode, because so we have the original circuit, we have the original model, still almost the same. So let me, yes, base, collector, emitter, and we have here the IC, IS exponential VBE over VT, and here is VBE. But now there is a forward junction between the base and the collector, so we should have another diode here. Okay, and here is another way to understand why IB is increasing and why IC is decreasing. So this is IB, and this is IC. Yeah, this is IC. So just look in here, IB will come at this point, this node, and go down. So the current here is equal to IB as well. But now IB will be equal to that one plus that one. So here is I1, for example, and here is I2. Okay, so originally, so IB equal to I1 plus I2. Originally it was only I1. So this is the extra portion. Yeah, this is the extra portion added. And the IC originally is equal to this portion, which is IS. This is I'm sorry, this is not IC now. So this is let's call it IC node. Yeah, that's good. That's a good name. IC node. IC before J2 becomes forward. So this is IC node when J2 is reverse or not conducting, off. Okay. So this is called the IC. This is equal to IC. What color are you using? Yeah, IC node. So we have here one in that way, and here I2 minus IC. This is going in. IC not minus, yes, minus I2. So this is, how can I say this? The decrement, we can say. So one current, which is I2, is added somewhere and decreased in another way with IC. Okay, so that's the basic mode that we're gonna use, at least for 10 minutes, as we'll see now, to solve diode, transistor circuits. Okay, so let's take two examples. So example one. Okay, we have here a circuit. Call this RC equal to 3 kilo ohms. Okay, and there is a constant current source equal to 10 microamperes. Okay, so this is an NPN transistor. Okay, has IS equal to 10 to the power minus 15 and beta equal to 100, and it's in active region. This is one of the givens. And it says find VBE and this is not and at all. And VC. So VBE is unknown and VCE is unknown. Okay, so let's do that. Okay, first of all, this is IB. That's sure, which is the same as this current. So IB, it's the solution now, equal to 10 microamps. Very nice. Okay, so we are in active region, so IC equal to beta IP. Remember, we can't use this equation in saturation. Okay, but since we are inactive as given in the question, so we can use it. So 100 multiplied by 10, it will be 1,000 microamps. It's just 1 milliamps. Very nice. Okay. We know that IC equal to we didn't draw this. Okay, that's fine. IC equal to IS exponential VBE over VT. And from now on, we will neglect the one. Another thing here, I will assume VT here is equal to 25 millivolts because this question or this problem or this circuit I pulled it from another book. You remember, guys, in our first lecture, I said that we have Razavi's book, which we were using in the diode, and we have Sidra book, Adil Sidra book. Okay, another book. So this is from the Sidra's book. Okay. So VT is equal to 25 millivolt. I'm just wanna be, the same page as this book, so I just assume the same assumption. But you can, of course, solve it with 26. That's very fine for me. Okay. So we have IS, VB is not known, VT is 25, and IC now is 1 milliamps. So from this, VBE is equal to VT ln IC over IS. Okay, and if you substitute, it will be 690.7 millivolts. So this is the first requirement. Now VCE. Now let's till this moment, by the way, we didn't use something. It is just we used that this current is equal to IB. Okay. Now let's draw the equivalent circuit. So let's draw this circuit in another way after substituting this symbol by its equivalent circuit. So its equivalent circuit, we have base, we have collector, and we have Mr. Emitter. Okay. Between the base and the emitter, we have the diode. And now we get the voltage on the diode equal to 690, 0.7 volt, millivolt, I'm sorry. And we have here, this is active region. So we will not draw something in between the collector and the base because it's active. Here is IC. Okay, here is I. Now we draw other parts of the circuit. So let's take terminal by terminal. So we have here first is a collector, for example. So this is a collector. Between the collector, I'm sorry, the collector is connected to a resistor called RC. Then this resistor is connected to a voltage source 5 volt. Just like a point which has 5 volt. You can draw it in that way. Okay. So that means there is a point here that has a node in the network that has 5 volt. Okay. So let's have a check for anything that we did. So we did also this node here. Now let's go to the base. This is the base. The base is connected to current source 10 microamps. And this current source is connected to 5 volt. Now someone will say, oh, we have two sources now. No, it's just one node, so I can just connect them, but I don't want the drawing to be bad. If you have two nodes in any circuit that has the same voltage, you can just connect them with there is a short between them. It's the same node. Okay. Now, and finally, the emitter is just connected to the ground. That's very easy. Okay, that's it. So we replaced this circuit by this circuit. Then you can solve now. So this is VC. This node has a voltage called VC. So VC equal to, and this is, remember, IC is equal to 5 minus ICRC. 5 minus IC is 1 milliamps multiplied by RC, which is 3.3 kilo ohms. And very good thing here about this, you will find all the time that you usually have resistors in kilo ohms and the currents in milli. So milli will cancel kilo. So you don't need to convert, to ohms or milliamps to amps, because they will cancel each other most of the time. Okay, so VC will be equal to, I'm sorry, this is 3 kilo or 3 kilo ohms. I'm sorry, 3 kilo ohms, not 3.3. Okay, so based on that, VC will be equal to 2 volts. Now let's check, because we know it's active region, right? So in active region, we know VBC should be off, okay, less than 0.4. Okay, so VC is equal to 2. VBE, let's see. VBE is equal to VB minus VE. Any voltage difference between 2 points is equal to the voltage of this point minus the voltage of this point. So this is base, this is the emitter. And we know that VBE between is 690.7 volt. VE is 0. So this is 0 here. So this is equal to VB. 690.7 millivolt. So VBC is equal to, let's convert this to volts, volt. So 607 minus 2, this is negative. So J2 is reverse or off as we require. This is just a check, because from the givens, this is active region. So it must be, your number should give something conform with this. So it should be active region. So the G2 should be reversed. Okay, let's have another example. This is clear, guys? Any questions? So let's have another example. Let's do it in the same page here, because they are related. So I'm gonna make a very small change. Okay, so it's the same example, but now Instead of the current source, we're gonna put a resistor, 5 volt. And for this one, as I said, the equivalent circuit, if you feel that the circuit is, you know, cumbersome for you, you can replace the transistor by the equivalent circuit. But believe me, you can work without it since you know the equations. Okay, so for this one, so we did one with the equivalent circuit. This one will not do with the equivalent circuit. So here we have 5 volt, RC still 3 kilo ohms, RB is equal to 431 kilo ohms, very big one. Okay, and usually you'll find that the resistors in which IB is flowing for very big, because IB usually very small. Okay, why is this? Because is a base region in the transistor is very thin, so very small contribution from this base in the current. Yeah, the whole current. Okay, so let's also find again same transistor, so same as the previous transistor in example 1. So we have, so this is example 2. So we have IS equal to 10 to the power minus 15, beta is equal to 100, and the still active region. And again, find VBE and VCE. Okay, let's do that. We replaced now the current source by a resistor. Okay, so now this is VBE. I will not draw the equivalent circuit, I will just use the circuit. Okay, so this is base, this is emitter. So the voltage between them is called VBE. Okay, so IB equal to 5 minus VBE divided by RB. Remember, IB is flowing in that direction, so it's equal to this one minus this node over the resistor value. VBE and IB is unknowns. In example 1, IB was known. In this example, no, it's not known. So just to stop at this, let's continue. IC equal to beta IB. So beta over RB 5 minus VBE. And IC is still unknown again. And VB is still unknown and IB is still unknown. But IC is equal to IS exponential VBE over VT. And now let's look at this equation in here. How many unknowns in it? It's just one unknown. So in principle, we can solve it and get VBE and get any other parameter we lack, like IC or IB. So let's try to do that. So let's put VBE in some side and all the knowns in another side. Remember, everything is known here except VBE. RB is known, 431 kilo ohms. Beta is 100. 5 is 5, of course. IS is 10 to the power minus 15. VBE is still our unknown, still one unknown, and VT is 25 millivolts or 26, whatever it is. I will tell you in the exam what value to choose. Okay, good. So let's try to do that. So RB over so if we multiply by RB divided by beta, so this will be 5 minus VBE equal to RB IS over beta exponential VBE over VT. So VBE is equal to 5 minus this stuff, RBIS over beta exponential, this is VBE over VT. But again, we have still VBE in one side and another VBE that's the same side in the other side. So, and of course we cannot, just like the diode, if you use the accurate model of the diode. So this is nonlinear equation. So you can't separate variables. I mean, you can't have, VBE in one side equal to something, and here is some constants or known in the other side. You can't have this. It's not linear. And that's a problem with using the large signal model or the general model. Okay, is that some circuits you have to do iterations, just like the diode. And in this particular example, if you do the iterations, actually you will get the same as the previous question here. So IB will be, everything will be the same. So the solution of, let me write this down. The solution should be using iterative method to solve, let's call this equation 1, to solve the equation 1, which is non-linear. The solution, if you do that, IC will be 1 milliamp, IB will be how much? 10 microamperes. VBE will be the same. Everything is the same. 690.7 millivolt. And of course, VC will be 2. Actually, this was a question that the original question was that if you replace the current source with a resistor and you want to get, and the resistor is unknown, and you want to get the same point of operation, which means same IC, same IB, and same VBE, same VCE, what would be RB? Okay, so I solved RB, then I tried to solve it from the beginning and found it to be nonlinear. Okay, and that's the problem with using, as I said, the large signal model. So we need a simplified model now to deal with our transistors, just like what we did with the diodes. Okay, so just like what we did with the diodes, okay, we tried first the accurate model. We found that we will use iterations all the time. This will make our solution cumbersome. Okay, and it will consume time. Also, the solution will be accurate. So we replace this accurate model with some approximations, which were the constant voltage model 0.7, and also the ideal model, in which you don't have any voltage drop on the diode. Same will be here. Okay, so let's see. Although it's still not that simple like the ideal voltage model or the constant voltage model of the diode. So let's see the simplified model. Okay, and actually they called DC model. So this DC transistor model. And from the name, it has restrictions. It's only for DC operation. So this is the caveat here. The previous models that we just found that it's bad, or not bad, it's very accurate, but of course you will lose time, okay, because you have to make iterations and stuff, because you will deal with nonlinear equations. This guy is a bit simpler. You don't need this nonlinear stuff, okay? But of course, it's not as accurate as the first one. Okay, we will make, and by the way, the accuracy is, is a little bit bad. But it's you know it's easy to visualize just by a piece of paper and a pen and a simple calculator what's gonna happen, you know, and what will be the operating point of the transistor, what will be IC, what will be IB in a very short time. Okay, but the caveat here is that it's valid for DC operation. If the inputs has some sort of AC component, you can't use it. Only for DC. Okay, so let's see what's actually this model will be. So first, for active region. For active region. So what we have for active region? We have many stuff actually. So we have IC equal to beta IP. We have IE equal to IC plus IB. Okay. You have VBE equal to 0.7. This will not change. This I will okay in the last I will say this. And what else we have? VBE, yeah. And VBC should be larger than or less than 0.4. So this means it should be J2 should be off. Okay, off means either reverse or even weak forward, as I said, something like this in that region here. Okay, this is active region. Is there an equivalent circuit for it? Yes, there is an equivalent circuit. Let's draw it. So the equivalent circuit would be something like this. We have again the 3 terminals. This guy. You can replace the transistor with this 3 terminals here. This is IC, and this is 0.7. It's equal beta IP. This is IP. And this is IC, collector base emitter. So you can remove the transistor and put this circuit instead of it. And of course, connect the remaining of the circuit you have. Also, as we will see later in this lecture, and as we have seen, it's it's very easy to use just the circuit with the original symbol. Okay, so not that hard. So this is an active region. How about saturation region model? So some equations will change, some are not. So this is usually not changing. This is not changing, but these two will change. So so VB is still 0.7. Okay. IC over IB is less than or equal to beta. Must be like this. If you find IC over IB larger than beta or something, of course this will be wrong. If it's a saturation and equal, this means you are on the on the edge, just between active and saturation. Okay, VCE equal to 0.2, and if so, this is called deep saturation. Sometimes is assumed 0.3, and in that case, it's edge saturation. And in that case, IC will be equal to beta IP still, or IC over IB is equal to beta. This will be mentioned in the question, so don't worry about that. What number we should assume. Okay. So these are the, and still of course IC, this is all the time IE is equal to IC plus IB. This is not changing as well. Okay, yeah. One, and what is the equivalent circuit? The equivalent circuit will be something like this. And this is VCE. Yeah. So basically, we will not be interested in solving, you know, and I'm sorry, this is the base, in bringing or calculating the current between the collector and the base. So we can safely assume there is open, although it's not open. Okay, because we are not interested. And actually, as I said, we will not even try to do this. If it's really cumbersome circuit, you can use it. Okay, but since we are not dealing with this current between the collector and the base, we will just assume open. Although there is a current flowing. Okay, and this is 0.2 or 0.3 based on the situation, if it's deep saturation or edge saturation. Yeah. One final remark here. There is another region called cutoff region, and you will see this quite often. Cutoff region. So if we draw the characteristics between VCE and IC, we said it is something like this. And we said then we go to the active, I'm sorry, saturation. Okay, and I said that in this region saturation here, VCE is between 0.1 to 0.3. But we didn't say zero, although it's ended at the zero, right? Because at zero, there is no current. If VCE is zero, IC is zero, and the IB will be zero. So there is another region, it's also just a point, not a region, which is called the cutoff. This is cutoff, in which everything is zero. I'm sorry, every current is zero, not everything. So here IC equal to IB equal to IE, everything is zero. Okay. Here you will find that J1, which is the base emitter junction, is off. But off junction like a diode. So when I say junction is off or diode is off, that means VBE is less than 0.7. So looks like VBE is equal to 0.7 is a rule, is a condition for both saturation and active. Whenever you have current, you must have VBE is equal to 0.7. And like this model. Okay, so these are the three regions and their equivalent model. Now let's take some example. So let's have examples now. Okay, that's fine. So let's see. I will also do that example with the equivalent circuit, but then I will not use it. But it's for you. If you find it, cumbersome to use the circuit with the original symbol of the transistor, use the equivalent circuits. That's fine. So we have here some resistors. So RC is RC 4.7 kilo ohms. RE is 3.3 kilo ohms. Beta is 100. And they usually call the transistor Q. So, I mean, if you look at the internet and you find a symbol of transistor with Q, this is the name. So usually we call the transistor Q. Why? I don't know. Okay. And this is 4 volts. Okay. So let's draw the equivalent circuit before we delve into the solution. Here, the question is find the Q point. Q point means find everything. Find IC, find IB, find VBE. No, not VBE. VBE will be no. Okay, VCE. This is Q point. Okay. Point of operation of the transistor. So let's solve it. So before we solve it, let's first draw the equivalent circuit. So we have 3 terminals, base, collector, emitter. Okay. And between the base and the collector, we have, as we said, this small battery, 0.7. And we have here a current source, beta IP. Okay. Let's now continue with the other part of the circuit. So this is the emitter. Between the emitter and the ground, there is, let's have a ground like this. Between the emitter and the ground, there is RE. RE. Of course, same value, 3.3 kilo ohms. This is a collector. Between the collector and this 10 volts, there is RC. So let's have here, this is the battery. You can put a node or draw a battery, it's up to you. This is a 10 volt battery, and we have RC. RC. 4.7 kilo ohms. And this is the base. And between the base and the ground, there is another battery of 4 volts. 4 volts. Now, the solution procedure. It's not mentioned in the question here if it's a saturation or active or even cutoff. Okay, we will do something again similar to the diodes. We will look into the circuit, try to figure out if it's active or saturation or cutoff, then assume, make some assumption, and prove the assumption is correct or disprove it or prove it as incorrect. Okay, then we go to another region. And luckily, this procedure in only 3 times, not luckily, it's even harder than the diode, I'm sorry. Yeah, the diode is on, either on or off. So you have, if it's not on, it will be off. If it's not off, it will be on. Here, if it's not active, it will be saturation. If it's not saturation, it will be cut off. Okay, so we have, extra step. Okay, so we'll assume, yeah. Just one note here is it's really hard to see by just looking at the circuit if it's saturation or active. But you can anticipate if it's cut off or conducting, which means active or saturation. I mean, there are currents. Because we can anticipate from this loop here if there is enough voltage for VBE to drive this junction into forward or not. Of course, it needs 0.7. So that's some hint for the cutoff region. Okay, so let's solve this question in here. Or so let's assume it's active. Assume active. Which means J2 is off. So VBC should be less than 0.4. Or even reverse. Okay, so let's do that. So nothing is known here. So we know this point here has a voltage of 4, and there is a 0.7 drop. So this one is 4 minus 0.7, and this is IE. So VE is equal to 4 minus 0.7, 3.3 volt. So IE equal to 3.3 volt minus 0 volt, which is the ground, over 3.3 kilo ohms. So this will be 1 milliamperes. Very simple. Okay, this is IE. Now IC equal to beta over beta plus 1 IE. So beta is known with 100. And IE now is 1 milliamperes. So this guy will be 0.9 or whatever. IC will, yes, 0.99 milliamps. And here is another, observation. Usually in active region, IE and IC are very close because beta is much, much larger than 1 all the time. So beta over beta plus 1, it's just like 1000 over 1001. It's really, close, very close to 1. Okay. So this is IC. IB is very simple, IC over beta. So just to divide this by 100. So it will be, if we divide it by 100, it will be very small. So let me just write it. Okay, it's not here as well. So it will be 90, I think 99. Yeah, 9.9 micro amperes. Okay. Now VCE. Okay, let's look at the circuit in here. Okay. This is VC. This is 10. And the current flowing here is IC is known now. So VC is equal to this point, which is 10, minus ICRC. VC is equal to 10 minus ICRC. 10 minus IC is 99 milliamperes, and RC is 4.7 kilo ohms. That's good because milli will go with kilos. So VC will be equal to 5.347 volt. Now, the moment of truth. Is it really active region or not? So we should calculate VBC, which is VB minus VC. VB, as we saw here, it's 4 volts. And VC, we just calculated. Okay, so this will be minus something, minus 1.347, less than 0. J2 is reverse, as we anticipated, or predicted, or assumed. So the assumption is correct. So thank you very much, and see you on Tuesday. Bye-bye.